students, welcome to the lecture on gas processing, and after this lecture we will be able to learn the following objectives. Understand the process modules in gas processing, define the natural gas sweetening, explain the natural gas origin and composition, discuss the gas sources, describe the characteristics of natural gas, explain natural gas properties, define the select optimal schemes for gas processing plants. Let's start with the concept of gas processing. Natural gas processing consists of separating first all impurities found including acid gases, water vapor, inert gases. This stage is called gas treatment. Sweetening of sour natural gas is the initial purification step which takes care of the removal of acid gases, H2S and CO2. Amine treatment, physical methods and others are discussed. Gas dehydration is carried out next using glycols TEG or solid desiccants for gas dehydration. Conditions leading to hydrates formation are highlighted. Chemicals for hydrate inhibition are recommended. Gas processing is the second and most important stage, is concerned with the recovery and extraction of NGL from natural gas followed by fractionation to separate components. Modern gas processing plants use cryogenic low temperature distillation process based on the expansion of the gas through a turbo expander. A fractionation column called demanthanizer follows. Methane, the residue gas, and NGL are the products from this column. Fractionation of NGL requires the use of a number of distillation columns for the separation to the desired components and products. There are primarily three sources for raw natural gas. These are recognized as crude oil wells, gas wells, condensate wells. Natural gas that comes along with crude oil is normally known as associated gas. It can exist separately from crude oil, forming what is known as a gas cap or dissolved in the crude oil. Natural gas from gas wells and from condensate wells in which there is little or no oils termed, on the other hand, non-associated or free gas. Gas wells differ from condensate wells since the former type produces raw natural gas only, while the latter one produces natural gas along with very light fluid hydrocarbon known as natural gasoline because it has a high octane number.
Natural gas plays a crucial role in the world's supply of energy. As a global leader in all aspects of natural gas processing, Black & Veatch provides process design and engineering, procurement and construction services.
Black & Veatch has extensive experience in a wide range of processes, be it open art, third-party technologies, as well as our own Black & Veatch developed proprietary processes. That breadth of knowledge gives us the ability to analyze each client's situation, each project, and come up with the right flow sheet and optimize it for their application.
Since many of our professionals have experience working in organizations similar to our clients, they understand the business drivers and the facility's goals. With more than 3,000 assignments in over 40 countries, we deliver safe and reliable solutions to our clients.
Black & Veatch has a depth of experience with many international partners. But what is special is there is a valuable history with Phoenix Park Gas Processors Limited. We've been able to improve at each stage of our projects, and we've been able to improve one project beyond the achievements of the other. I think what I value most about working with Black & Veatch is the relationships we build with the engineering team.
Black & Veatch brought their value of their expertise, their knowledge, their experience in engineering, procurement and construction. They were able to design the plant very efficiently, meeting all the standards that we requested and more. The project diversified our product slate. So before we had mixed butane and After the completion of the project, we can now increase our product slate to isobutane, mixed butane, as well as normal butane. And it gives us the flexibility to split and sell different products and put different plants downstream. So it actually grows and expands the business.
From gas treating to sulfur recovery, NGL recovery to fractionation, Black & Veatch understands the impact of decisions on other parts of the plant and to the bottom line.
Black & Veatch has something to offer all along the value chain for gas. So we can do just a little part of it, we can do the whole thing, we can do any mix that people really need in the way of services.
As an industry technology leader, Black & Veatch holds numerous patents. Our proprietary Preco technology was pioneered for liquefaction of natural gas over 40 years ago. We've continued to enhance this unique process to give our clients the lowest operating costs as well as the lowest equipment count.
We've taken our experience with single mixed refrigerant processes and incorporated that into our new technology, Preco C2. Using the mixed refrigerant, we're able to get much colder than a conventional refrigeration system, which allows us to get the recoveries in a gas processing facility without the need for as much or perhaps any feed compression, so that we can give a much lower capital and operating expense for our client.
Black & Veatch's new technology, called LPG Plus, extends the operating range of LPG recovery. This technology expands our capabilities and offers solutions to our clients with natural gas or off-gas streams, high or low pressure feed gases, as well as rich or lean gases.
LPG Plus, compared to conventional turbo expander technologies, can represent significant savings in compression horsepower.
You can count on us to tailor the right solution to meet your goals. We'll deliver safely, on budget, and on schedule.
Let us now discuss the process modules. The first unit module is the physical separation of the distinct phases, which are typically gas, liquid, hydrocarbons, liquid water and solids. Phase separation of the production stream is usually performed in an inlet separator. Hydrocarbon condensate recovered from natural gas may be shipped without further processing but is typically stabilized to produce a safe transportable liquid. Unsterilized condensates contain a large percentage of methane and ethane, which will vaporize easily in storage tanks. Natural gas processing is acid gas treating. In addition to heavy hydrocarbons and water vapor, natural gas often contains other contaminants that may have to be removed. Carbon dioxide CO2, hydrogen sulfide H2S, and other sulfur-containing species such as mercaptans are compounds that require complete or partial removal. Condensate stabilization, the process of increasing the amount of intermediates C3 to C5 and heavy C+6 components in the condensate is called condensate stabilization. In other words, the scope of this process is to separate the very light hydrocarbon gases, methane and ethane in particular, from the heavier hydrocarbon components C+3. Stabilization process. Stabilization of condensate streams can be accomplished through either flash vaporization or fractionation. Stabilization by fractionation. Stabilization by fractionation is a detailed process, very popular in the industry and precise enough to produce liquids of suitable vapor pressure. Now moving on to the next topic, we will study the natural gas sweetener. Hydrogen sulfide, carbon dioxide, mercaptans and other contaminants are often found in natural gas streams. Gas sweetening processes remove these contaminants so that the gas is marketable and suitable for transportation. The removal of H2S from natural gas is accompanied by the removal of CO2 and COS if present, since these have similar acid characteristics. Desulfurization processes are primarily of two types: absorption on a solid dry process and absorption into a liquid wet process. Both the adsorption and absorption processes may be of the physical or chemical type. The dominant sulfur removal complex, train, amine scrubbing, Claus unit, Scott type tail gas treating, a Bevan Stretford tail gas system, amine scrubbing. Amine gas treating refers to a group of processes that use aqueous solutions of various amines to remove hydrogen sulfide H2S, mercaptans and or carbon dioxide CO2 from gases through absorption and chemical reaction. It is a common unit process used in refineries, petrochemical plants, natural gas processing plants and other industries. The process is also known as acid gas removal and gas sweetening because they result in products which no longer have the sour, foul odors of mercaptans and hydrogen sulfide. A typical amine gas treating process includes an absorber unit and a regenerator unit as well as accessory equipments. Sulfonol process. A sulfonol process is a regenerative process developed to reduce H2S, CO2 and COS and mercaptans from gases. The sulfur compounds in the product gas can be reduced to low ppm levels. This process has been developed specifically for treating large quantities of gas such as natural gas which are available at elevated pressures. The sulfonol process is unique in the class of absorption processes because it uses a mixture of solvents which allows it to behave as both a chemical and a physical adsorption process. Very wide ranges of treating pressures and contaminant concentrations can be accommodated. Natural gas pipeline specifications are easily met. Removal of organic sulfur compounds is usually accomplished by the solvent circulations as set by H2S and CO2. In LNG plants, a specification of 50 ppm CO2 prior to liquefaction is attained without difficulty. Features: removal of H2S, COS and organic sulfur to natural gas pipeline specification, low steam consumption and solvent circulation, low corrosion rate, selective removal of H2S in some natural gas applications, smaller equipment due to low foaming tendency. Claus sulfur recovery processes. Hydrogen sulfide H2S is a smelly, corrosive, highly toxic gas. It also deactivates industrial catalysts. H2S is commonly found in natural gas and is also made at oil refineries, especially if the crude oil contains a lot of sulfur compounds. Because H2S is such an obnoxious substance, it is converted to non-toxic and useful element sulfur at most locations that produce it. Description of the Claus process. First, the H2S is separated from the host gas stream using amine absorption. Then it is fed to the Claus unit where it is converted into two steps. As thermal step, the H2S is partially oxidized with air. This is done in a reaction furnace at high temperatures 1000 to 1400 degrees Celsius. Sulfur is formed, but some H2S remains unreacted and some SO2 is made. Burner: 2 H2S plus 3 O2 is more than 2 H2O plus 2 SO2. Catalytic step: the remaining H2S is reacted with the SO2 at lower temperatures 450 degrees Fahrenheit, about 200 to 350 degrees Celsius, dew point of S to prevent condensation on the catalyst to make more sulfur. A catalyst is needed in the second step to help the components react with reasonable speed. Unfortunately, the reaction does not go to completion even with the best catalyst. For this reason, 2 or 3 stages are used, with sulfur being removed between the stages. Engineers know how different factors like concentration, contact time and reaction temperature influence the reaction, and these are said to give the best conversions. Reactor converter. 2H2S plus SO2 is greater than 2H2O plus 3S. Condenser outlet must be 350 degrees Fahrenheit more than melting point of S to prevent the formation of solid S. Inevitably, a small amount of H2S remains in the tail gas. This residual quantity, together with other trace sulfur compounds, COS and CS2, formed in the burner side reaction, is usually dealt within a tail gas unit. The latter can give overall sulfur recoveries of about 99.8%. Sulfur plant tail gas cleanup processes, because of the more stringent requirements of pollution control, requirements for tail gas cleanup processes are developed. Scott process. The closed tail gas is heated to about 570 degrees Fahrenheit and reacted with H2 over a cobalt molybdenum catalyst. The entire COS, CS2 and SO2 in the closed unit of gas are converted to H2S by the following reaction. COS, CS2 and SO2 plus H2 is greater than H2S plus CO2 plus H2O. These reactions are highly exothermic. The hot gas from the reactor is cooled in a waste heat boiler and finally quenched in a water cooling tower. The final stage involves the selective absorption of H2S in an amine solution, normally DIPA. The vent gas from the Scott absorber typically contains 200 to 500 ppm of H2S. This vent is normally incinerated before discharging to the atmosphere. The rich amine is stripped in a conventional manner and the H2S rich stream is recycled back to the front of the Claus plant. The Claus plus Scott processes combine to remove 99.5% of the S. Bevan tail gas unit. A hydro-treating reactor converts SO2 in the off gas to H2S. The generated H2S is contacted with Stratford solution, a mixture of 222 vanadium salt, anthraquinone disulfonic acid ADA, sodium carbonate and sodium hydroxide in a liquid gas absorber. Let's know the meaning of natural gas and origin and composition. Natural gas exists in the nature under pressure in rock reservoirs in the Earth's crust, either in conjunction with and result in heavier hydrocarbons and water or by itself. It is produced from the reservoir similarly to or in conjunction with crude oil. Natural gas has been formed by the degradation of organic matter accumulated in the past millions of years. Two main mechanisms, biogenic and thermogenic, are responsible for this degradation. Biogenic gas is formed at shallow depths and low temperatures by the anaerobic bacteria decomposition of sedimentary organic matter. In contrast, thermogenic gas is formed at deeper depths by thermal cracking of sedimentary organic matter into hydrocarbon liquids and gas. This gas is cogenetic with oil and is called primary thermogenic gas, and thermal cracking of oil at high temperatures into gas, secondary thermogenic gas and pyrobitumen. Biogenic gas consists almost entirely of methane. In contrast, thermogenic gas can also contain significant concentrations of ethane, propane, butanes and heavier hydrocarbons. Knowing whether a natural gas show is biogenic gas or thermogenic gas can have critical implications for the presence of liquid hydrocarbons in a basin. Gas geochemistry readily reveals whether a gas is biogenic or thermogenic. Natural gas is considered dry when it is almost pure methane, having had most of the other commonly associated hydrocarbons removed. When other hydrocarbons are present, the natural gas is wet. The composition of natural gas varies depending on the eld formation or reservoir from which it is extracted. Since the composition of natural gas is never constant, there are standard test methods by which the composition of natural gas can be determined and thus prepared for use. Sources. Natural gas produced from geological formations comes in a wide array of compositions. The varieties of gas compositions can be broadly characterized into three distinct groups. Non-associated gas that occurs in conventional gas eld, associated gas that occurs in conventional oil eld, and continuous or unconventional gas. Some types of unconventional gas resources include tight gas or tight sand gas, which is found in low permeability rock, coal bed methane (CBM), which is natural gas that has been formed along with the geological processes that formed coal, natural gas from geopressurized aquifers, which refers to gas dissolved under high pressure and at high temperatures in brines located deep beneath the Earth's surface, gas hydrates, which are ice-like structures of water, and gas located under the permafrost, and deep gas, which is found at levels much deeper than conventional gas. Although there is no scientific consensus, some believe deep gas originated from inorganic sources and that it exists everywhere as a result of the geological processes that formed the Earth. Of the conventional gas sources, the one most important to the gas transportation industry is coal bed methane. Non-associated gas. Non-associated gas, sometimes called gas well gas, is produced from geological formations that typically do not contain much, if any, higher boiling hydrocarbons, gas liquids than methane. Non-associated gas can contain non-hydrocarbon gases such as carbon dioxide and hydrogen sulfide. Non-associated gas is directly controllable by the producer. One just turns the valves. The gas flows up the well under its own energy, through the wellhead control valves and along the flows line to the treatment plant. Treatment requires the temperature of the gas to be reduced to a point dependent upon the pressure in the pipeline, so that all liquids that would exist at pipeline temperature and pressure condense and are removed. Associated gas. Associated gas is produced during crude oil production and is the gas that is associated with crude oil. Crude oil cannot be produced without producing some of its associated gas, which comes out of solution as the pressure is reduced on the way and on the surface. Properly designed crude oil well completions and good reservoir management are used to minimize the production of associated gas so as to retain the maximum energy in the reservoir and thus increase ultimate crude oil recovery. Crude oil in the reservoir with minimal or no dissolved associated gas is rare, and as dead crude oil is often difficult to produce as there is little energy to drive it. After the production fluids are brought to the surface, they are separated at a tank battery at or near the production lease into a hydrocarbon liquid stream, crude oil or gas condensate, a produced water stream, brine or salty water, and a gaseous stream. The gaseous stream is traditionally very rich gas in natural gas liquids, NGLs. Natural gas liquids include ethane, propane, butanes, and pentanes, and higher molecular weight hydrocarbons 6C+. The higher molecular weight hydrocarbons product is commonly referred to as natural gasoline. When referring to natural gas liquids in the natural gas stream, the term gallons per 1,000 cubic feet of gas is used as a measure of hydrocarbon richness. Depending on its content of heavy components, natural gas can be considered as rich 5 or 6 gallons or more of recoverable hydrocarbons per cubic feet, or lean less than 1 gallon of recoverable hydrocarbons per cubic feet. However, the terms rich gas and lean gas, as used in the gas processing industry, are not precise indicators of gas quality but only indicate the relative amount of natural gas liquids in the gas stream. Coal bed methane. Coal bed methane is the generic term given to methane gas held in coal and released or produced when the water pressure within the buried coal is reduced by pumping from either vertical or inclined to horizontal surface holes. During the coalification process, a range of chemical reactions takes place that produce substantial quantities of gas. While much of this gas escapes into the overlying or underlying rock, a large amount is retained within the forming coal seams. However, unlike conventional natural gas reservoirs where gas is trapped in the pore or void spaces of a rock, such as sandstone, methane formed and trapped in coal is actually absorbed onto the coal grain surfaces or micropores and held in place by reservoir pressure. Characteristics of natural gas. Composition and properties. Natural gas is a hydrocarbon consisting mainly of methane, although it usually also contains a variable percentage of nitrogen, ethane, CO2, H2O, butane, propane, mercaptans and traces of heavier hydrocarbons. Methane is one carbon atom joined to 4 hydrogen atoms, CH4, and can constitute up to 97% of natural gas. Natural gas phase behavior. The natural gas phase behavior is a plot of pressure versus temperature that determines whether the natural gas stream at a given pressure and temperature consists of a single gas phase or two phases, gas and liquid.
Natural gas has enormous potential as a versatile energy source. While it's had a history of powering electric generators and heating stovetops, it's growing in use as an efficient fuel that also powers cars and trucks. But what exactly is natural gas? Natural gas is a naturally occurring chemical, primarily made up of methane, CH4. Its purity makes it an environmentally friendly fuel. Methane does not leave a residue when burned, so its emissions do not react with sunlight to create smog. The natural gas we use today began as microscopic plants and animals living in the ocean tens of millions of years ago. As they thrived, they absorbed energy from the sun, which was stored as carbon molecules in their bodies. When they died, they sank to the bottom of the sea and were covered by layer after layer of sediment. As these plants and animals became buried deeper in the earth over millions of years, heat and pressure began to rise. The amount of pressure and degree of heat transformed the biomatter into natural gas. After natural gas was formed, it tended to migrate upward through tiny pores and cracks in the surrounding rock. Some natural gas seeped to the surface, while other deposits traveled upward until they were trapped under impermeable layers of rock, such as shale or clay. These trapped deposits are where we find natural gas today. In 1859, Edwin Drake drilled the first commercial well in Titusville, Pennsylvania, striking natural gas and oil. This is considered by many to be the beginning of the natural gas industry. For most of the 1800s, natural gas was used almost exclusively as a fuel for lamps. Because no pipeline network existed to transport large amounts of gas over long distances, most of the gas was used to light local city streets. It was moved through small-bore lead pipe. Then, in 1885, Robert Bunsen invented a burner that mixed air with natural gas. The Bunsen burner showed how gas could provide heat for cooking and warming buildings. After the 1890s, many cities began converting their street lamps to electricity, forcing gas producers to look for new markets. But the lack of mobility to transport gas to consumers was still an issue. In the energy industry, natural gas was originally obtained as a byproduct from oil production. Since it was viewed as too costly to produce, much of it was burned off by flaring at the wellhead. Improvements in metals, welding techniques, and pipe making during World War II opened natural gas to new markets thanks to pipeline networks. Throughout the 1950s and 1960s, thousands of miles of pipeline were constructed throughout the United States. Although natural gas was becoming economically attractive with a growing pipeline network, crude oil was still far more popular and more widely used as a source of energy. For years, the industry perception remained that supplies of natural gas were limited. Although natural gas had been discovered in tight rock formations called shale, it was deemed too expensive and difficult to harness. With advances in drilling technology, new solutions emerged that solve these issues. Horizontal drilling and hydraulic fracturing, commonly referred to as fracking, were introduced as innovative techniques to reach shale deposits and harvest natural gas. Originally pioneered in the 1940s and refined in the 1970s, these processes have revolutionized the
Natural gas properties. The properties of natural gas can be described as chemical and physical properties. Natural gas is colorless, odorless, tasteless, shapeless, and lighter than air. The natural gas, after appropriate treatment for acid gas reduction, odorization, and hydrocarbon and moisture dew point adjustment, would then be sold within prescribed limits of pressure, calorific value, and possibly Warb index, often referred to as the Warb number. The Warb index, calorific value divided by the specific gravity, gives a measure of the heat input to an appliance through a given aperture at a given gas pressure. Using this as a vertical coordinate and the m speed factor as the horizontal coordinate, a combustion diagram can be constructed for an appliance or a whole range of appliances with the aid of appropriate test gases. This diagram shows the area within which variations in the Warb index and the m speed factor of gases may occur for the given range of appliances without resulting in incomplete combustion, flame lift, or the lighting back of pre-aerate dames. Select optimal schemes for gas processing plants. Gas processing plants are an essential part of the energy industry and provide one of the cleanest burning fuels and a valuable chemical feedstock. The importance and complexity of gas processing plants have increased over the years due to their use as a feedstock source and their integration with petrochemical plants. Process scheme selection. The process selection study usually begins with a design basis to specify the general configuration of the plant and its outline requirements. These requirements consist of feed characteristics, especially H2S, CO2, and mercaptan concentrations, product specifications, including maximum concentrations of sulfur and CO2 in the products. Now, in the end, let us summarize what we have learnt in this lecture. Natural gas processing consists of separating first all impurities found, including acid gases, water vapor, and inert gases. Hydrocarbon condensate recovered from natural gas is shipped without further processing but is typically stabilized to produce a safe transportable liquid. Hydrogen sulfide, carbon dioxide, mercaptans, and other contaminants are often found in natural gas streams. Natural gas is a hydrocarbon consisting mainly of methane, although it usually also contains a variable percentage of nitrogen, ethane, CO2, H2O, butane, propane, mercaptans, and traces of heavier hydrocarbons. Non-associated gases produced from geological formations that typically do not contain much, if any, higher boiling hydrocarbons, gas liquids than methane.